Okay, I'm reading a little bit from the document in the Moodle, so you can also watch there if you want. So, today we're going to learn about something completely different, something new, something that you're going to learn in class only in about a week from today, which is an infinite potential well. Okay? In general, as the course goes on, we might move to more dimensions. Depends on, I don't know how fast we're going to learn. But as far as we talk about one dimension, the most simple potential is, well, let's write the Schrödinger equation. Minus h bar squared over 2m d dx squared and psi plus v of x psi of x is equal to e psi of x. This is the time independent Schrödinger equation, right? Good. So we can talk about different v of x. v1 of x can be 0. This we call free particle. And another one that we'll discuss today is v of x is equal to 0 if x is between 0 and L, and infinity else. What does it look like? Like this. Here I have the potential of infinity, and I'm bound to being here. Okay? I can put some axes if you want. This would be v as a function of x. And here it's infinity. Why are these the first two potentials that we learn about? Well, because they're the simplest. This one is just 0, not existing, and this one is 0, is either infinity or 0. As we go on, we can talk about other things. What's expecting you in the future? Well, something else that's expecting us in the future is 0 when x is between 0 and L, and plus or minus v naught else. If, meaning I could talk about something like that, where this is a potential well, but it's not infinite, it is finite, or something else which is going to be a potential barrier. After we do that, we can talk about v4 of x, which is going to be a harmonic oscillator. V of x is n omega squared x squared, something like that.
Right. 1/2.
Yeah, that's why I did this. You're bothered by that 1/2, right? Was anyone else bothered by it? A little bit. Okay. So it's gonna be like this. So these are the potentials we're gonna. These are the potentials we're gonna see. As you can see, they're all one-dimensional because it's easier. And we like easy things, right? And all of them we can use usually Cartesian coordinates, which are fun. Why are they called Cartesian?
For René Descartes.
Yes, very good. So Richard is going to talk about this and about this in the next course, and then we'll talk in the next class, and I'm going to start already by talking about this. Okay. What do we expect? Well, we expect the particle to be here and not here. Very simple, right? We're going to start with some equations, and I actually want to start with the time-dependent Schrödinger equation. So I have minus h bar squared over 2m psi double prime plus v of x psi is equal to, I always get confused with the minus here, but it is I h bar psi dot. So far so good. We know that we solve this through separation of variables. Now I want to first, when I'm talking about infinite potential well, I want to talk about two different scenarios. One is inside the well, and one is outside the well. Okay? Let's talk here inside and outside. I'm not exactly going according to the order here. I will soon go to this document. Outside the well, I have minus h bar squared over 2m psi double prime plus infinity times psi is equal to I h bar psi dot, or if you want, e psi. You still? I hate this. Sorry. Is equal to e psi. Like they could have just put it here, right? It's not like there's. Anyway. Now this is infinity. I can write it differently. You know what? I can write it infinity psi is equal to e psi plus h bar squared over 2m psi double prime. This is finite. And this is infinite, right? The only way that it is possible is if psi is 0, which goes well with my assumption that if here I have a potential barrier, I have a mountain, I have something blocking me so I cannot be here, so my psi is 0. I'm reminding you, psi has to do with the probability of finding the particle. The probability of finding the particle here or here or here is 0. Okay. What happens inside the potential one is, of course, way more interesting. What I have here is minus h bar squared over 2m psi double prime. This now, I'm not there yet. I'll get there soon. Plus 0 times psi is equal to I h bar psi dot. This I saw through separation of variables. Do you have any other classes here in this room? No? What?
I don't.
Okay. I want to know if other people fall here as well or just me. Okay, so I can write this as minus h bar squared over 2m. I can write psi of x t is equal to phi of x t of t. I'm pretty sure I did it already here, right? It's the kind of thing that's good to do more than once. Also, it doesn't take so long. So if I rewrite the same formula, I get minus h bar squared over 2m phi double prime times t is equal to I h bar t dot phi. I divide by psi. I get minus h bar squared over 2m phi double prime over phi is equal to I h bar t dot over t, and I call this as E. And here, for the time, I get t dot is t times I h bar E. So t is a e to the I h bar e t, which is a e I.
Shouldn't there be a division?
Wait, I made a mistake here, right? I made a mistake here. T dot is e over I h bar. Which gives me the minus here, and E is going to be over h bar. And if E over h bar I define it as omega, I get e to the e I omega t, where omega is going to be e over h bar. What I want to add here, I want to add here a subletter. What? I want to add here a small n, because there can be many different energies. I'm going to write it as En. And this En is going to affect both the time and the position, space, location, that. So here I have En, this is En, this is omega n and omega n. Okay? And I have a minus that I lost here somewhere. Good, this is the time. Now let's go to the position. Here I have our, I don't know, harmonic oscillator equation, right? Psi double prime is psi. When we talk about a free particle, what we like to do is writing it with exponents. When we talk about infinite potential, well, we prefer writing it as sines and cosines. Okay? Legitimate choice, I'm allowed to do whatever I want. This is what's acceptable to write because it's way more convenient. What I get here is psi double prime is equal to minus 2me over h bar squared phi. Did I do it correctly this time? So, and of course the e is still going to be En, which is why phi is going to be a sine something plus b cosine something, and of course sine and cosine is a very poor choice. A is a very poor choice because I already used a, right?
Yeah.
So C1 sine of, I'm going to do the square root of that. So I'm going to do square root of 2me over h bar plus C2 cosine of the same thing. What am I missing?
The x.
Very good. I'm missing the x here and the x here. Okay, and what I'm going to do now is I'm going to tell you that the psi is continuous. Psi must be continuous. This is going to be always, always, always true because psi represents something physical. Well, the probability to find something, the probability shouldn't jump from 0 to infinity. So, if I have here a potential well, psi here is two colors, remember these colors, good. Psi here must be 0, and psi here must be 0. And if here x is 0, and here x is L, it means what I have is
Boundary conditions.
boundary condition, and which of these two is, I know that psi of, phi of x equals 0 must be 0, which means that
The sign.
C2 is 0. Very good, I'm going to get here signs. Right?
Right.
These are different signs I can get here.
About the continuity property.
About the what?
About the continuity. So the actual physical thing that we're measuring is the probability to find a particle in different locations, right?
The actual physical thing is the location of the particle.
Yeah, it's the location of the particle, but we can also measure the probability, right? And
Yeah, if you do many checks, yeah.
if we say that the probability has to be continuous, then the integral of psi squared with absolute value should be continuous. But the integral of a discontinuous function is still continuous, so that doesn't prove that there isn't a jump in psi. You need some other argument for that.
Please repeat. You're saying, I can just tell you, psi is continuous. This is just a rule. I can tell you always.
Well,
We'll talk about the
that's
physics
true.
behind it. You can talk. This is more. The more to the more typical question for the lecture for Richard, but I'll still try and understand your question. You're saying if a function,
Okay.
if a
So
function,
draw for a second the function with a jump, right? That's not continuous. Yeah. So if you think of its integral, then the integral doesn't become discontinuous the moment you arrive at the jump. The integral of the function is still continuous,
right?
even though this function is discontinuous.
Correct.
So,
I'm not saying that the integral of psi is continuous. I'm saying psi is continuous.
yeah, I know, but I'm saying that to prove that, or like to arrive at the conclusion that psi is continuous, I don't think you can use that type of argument by saying that, well, if the probability is continuous, then the integral of
The probability is not the integral of psi.
psi squared
It is psi squared.
is the density.
The probability of finding the particle at an interval dx is psi squared dx. This is the probability of finding the particle here. It's not the integral, just this. If you, I can write it here with delta x. Then you won't see an integral here at all.
Yeah. But well, it is an approximation, right? At the end of
No, it's not an approximation. This is exactly the probability of finding the particle here.
it's a zero order approximation because when you look at the function
Right.
in a small interval,
It changes, right?
Then the integral over a small interval is close to multiplying by delta x.
Okay.
But technically, it's still defined as the integral.
Okay, this is all
Even
settled.
if the interval is small.
I think we'll talk about it another time, okay?
Okay.
And as I said, this is more lecture material. I'm just saying psi is always continuous. Always, always, always. No exceptions. Okay. So I got here my phi. And I want it to be, I use here one boundary condition to get rid of C2. I need to use another one,
Normalization.
which is gonna, I also have normalization. I also want to make sure that psi,
Ah, right.
before normalization, I want to get here something that will give me something really cool called quantization.
Right.
Right? Because if I want phi of x equals L must be 0, it is also, well, C1 is not important here. It means that sine of square root of 2me over h bar times L must be 0. So far so good? Which means that square root of 2me over h bar times L. We write it as En, right? We wrote it as En before. Let's continue with En. R and pi. Wait a second! That means that En is going to be N pi h bar over L squared over 2m. So my ENs are, well, n squared pi squared h bar squared over 2ml squared. What I did here is I used stuff that you already know and I applied it to a new system that you're not familiar with. Separation of variables you met in previous courses, you met in this course. The solution time you met. Applying the psi 0 outside, you did not see, but it makes sense applying it to this specific potential. Saying that psi is continuous is an argument I just told you. You must believe me. I'm your TA. I know. Therefore, I remain with this function. And when I require that psi will be 0 at both ends, I get a quantization. Now, something which is very tricky in quantum mechanics in general is what is the connection between different things we know about quantum mechanics. One thing we know is that we talk about probabilities. The other is that some energies are allowed and some are not. What is the connection between those two things, right? There's another one which you can be at a few places at the same time or something. How do all these things go together, right? So here we're seeing one thing. We just spoke about psi as a function describing the probability and density function, the square root of that, and it led us, requiring that it will be continuous, it led us to specific energies that are allowed. Okay? Should I show units of it? Not interesting, right? It's units of energy. What is tensivity?
Angular momentum.
Angular momentum is
Kilogram.
kilogram meter squared over MRV, kilogram meter squared over second, right? Good. I want to divide it by kilogram meter squared. That's it, right?
H bar should be squared, so the...
Thank you. You just saved me. So what I'm left here is with kilogram metal squared over metal squared, I get here metal squared. Omega second squared. Whoa, this is energy! It's like mv squared.
Right.
Good. Okay, what I'm left with is also normalization. The C1 is going to be square root of 2 over L, because the integral of sine squared between 0 and L is exactly L over 2. And I'm very scared right now.
And also we can define the wave vector, right?
The what? The wave function?
Wave vector. K.
Yeah, we can also define K. Yes. Would it make you happy? Okay, so you can do it. Now I can write that psi of x t is, well, it always was phi of x t of t, right? I'm going to write it as a summation over Cn phi n of x e to the minus I omega n t. I can write it differently and say that it's a Cn square root of 2 over L. L over 2? 2 over L. 2 over L. Sine of that thing, square root of 2 me over h bar x, and yes, I can define this as k, it will make Joseph happy, times e to the minus I e and t over h bar. This is a general solution. What I see here is that I can be at a few different states in the same time. Let's draw them for a second. You're going to see all this in the lecture, but first of all, it's good to see things more than once. Secondly, I can't really teach a problem here without giving you this background. Well, the first one is this. The second one is this. The third one is this. What do we see here? Well, first of all, I'm going to ask you the trivial question. How come psi can be negative?
Because we don't care, we care about the square.
Right, it can be negative, it can be imaginary. What we care about only is the absolute value scared, right? Okay. Secondly, you see that the more, the higher the energy is, the more I'll be like this, right? What happens when n, this is n is equal to?
0.
1. Aha! Something very annoying in general in this degree is that you need to see where n starts, where the index n starts, and it depends on every problem. We're going to talk about harmonic oscillator. It's going to be another system, but then the index n will start from 0. We're not there yet. What kind of harmonic oscillator? Here, if n is 0, E is 0, psi is 0, and we have no particle. So we start with n equals 1. Here we have n equals 2, n equals 3, and here n equals infinity, or goes to infinity. Equals, I beg. And it goes to infinity. Okay, let's talk some physics here. What does that mean? First of all, you see that every as we go up level, every level we go up, we have one more cross, one more node, whatever. You see that the parity changes, even, odd, even. Also, I see that if something has very, 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 very high energy, it goes like this all the time, right? So I expect that my chances of finding the particle to be equal. I might find it here, I might find it here, I might find it here. If the energy is very, very low, then I go back to a classic problem. A classic problem, well, I have more chances of finding it here than in the sides. Therefore, here is the peak. Of course, here, the fascinating thing here is that there's no chance of finding it exactly here. Just like there's energies that are allowed, there's places that are not allowed. The particle can be here, it can be here, it can go back and forth between them, it can never be exactly in between. So how does it go from here to here? I don't know. It does. So this was the infinite potential well, and it can be at a few states in the same time. All this was an introduction. How fun. Now I tell you, for example, that I have a system. It doesn't even need to be a harmonic infinite potential well. It can be whatever system it is. I purposely did not erase this one. Let's say I have, like, this is always true. Always, 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 right? The time dependent part always give me this exponent. The space is going to be another function. For me here, it is sines. It can be different things for different systems. And C is the fact that I can be at different energies, different ENs in the same time. Okay? Now I tell you that my probability, P1, because I have 4 questions, so I'm going to have P1, P2, P3, P4. I think 1, 2, 3. Okay, good. So P1 is P of E equals E1. What is the chance of... Oh, sorry. I forgot to copy this. That's what I do. I have here, you're given a certain wave function, x times t. I'm telling you that psi of x t is 1 over square root of 3 phi1 of x times e to the power of minus I e1t over h bar plus minus I over square root of 2 phi2 of x e to the minus I e2 times t over h bar. How I know? Minus I plus 1 plus I divided by 2 square root of 6 phi3 of x e to the minus I e3t over h bar. Meaning I would have 3 different functions in the same time. 3 different energies in the same time. Is that even possible? Yes, it is. Okay. Now what does that mean? How do I work with this? Now I can ask you what is the probability to find a particle at time t with the wave function psi1, with the energy E1. The probability is going to be exactly this absolute value squared, or this, or this. Okay? The probability of E to equal E1 is going to be 1 over square root of 3 absolute value squared, which is a third. The probability of E to be E2 is going to be minus I over square root of 2 times plus I over square root of 2 squared. Sorry, not squared. I times minus I is 1, I get here 1/2, right? What will be the chances of finding the particle with the energy E3? What do you ask? It is 1. Well, this minus is going to die anyway. So I get here 1 plus I over 2 square root of 6 times 1 minus I over 2 square root of 6. And this gives me, I have 1 plus I, 1 minus I is 1. Well, it gives me a 2 divided by 4 times 6. Why 12? 2 times 2. What? Wait. I have to say I haven't inside each time. Wait a second. Why does it here it says 16? Help me out. Oh, it says here square root of 12.
It should be 1 over 6 because the probabilities should sum up to 1.
Exactly, that's the punchline. This is 1 over 6. It's easy to see. What? Okay. 1 plus I. I guess there's a mistake in the question.
Yeah, probably. they should have divided by the square root of 12.
Exactly. I have your square root of 12. Square root of 12. Square root of 12. And I have your 2 times 6, which is exactly 1 over 6. And now you can see that P of finding it 1, 2, and 3, the sum over, I get your general formula if you want, it's going to be always, always, always true. The sum over Cn squared must be 1. What I could have done is, I could tell you, the chances of finding the particle at 1 is this. The chances of finding the particle at 2 is half. And other than that, I know that I'm not at higher than 3. What is the chance of finding the particle at energy E3? Well, 1 minus a third minus a half is 1/6.
And that is due to normal orthonormalization of the functions, right? Because if we wouldn't have, there would be mixed terms.
Yes. Okay. From here, let's go to questions about, well, here there's a general algorithm for finding what are the CNs. If you just spoke about orthogonality, right? How do I find orthogonality? How do I find it? Should I erase everything? Okay. Can you remind me your name? Is that one? No? Yes? Hi, Kai?
Hi.
Okay. So, can you see here? Not really, right? Here. You can see my finger now?
I can see that.
Now you can see, right?
Yeah.
This is this.
Half of this line is
This you can see.
yeah.
Okay. And after doing this, I'm going to erase this part. We have here a general algorithm of finding a particle. When we talk about let's talk about Fourier series, right? If I'm exactly in a superposition of this and this, so you're going to have 2 functions out of the Fourier series, right? But if I ask you, what are my different sine and cosine when this is my initial state, can psi be this at the beginning? Of course it can. It can be anything. What does it mean here? That I have some infinite sum of sines. How do you find this? Through Fourier series. Okay? When it's going to be another system, Fourier series is sine and cosines. Here my functions that I work with are sines. So it works with Fourier, right? What happens if I have something else? If I have something else, I have to break it apart and I have to find the eigenvalues, whatever, the coefficients of another set of functions that spans the Hilbert space. Oh, now I feel smart. I said the word Hilbert. So I'm reading now from the document. Whoever's at home can look there at the end of page 2. Given h and psi, I can solve h phi is equal to e phi to find en and phi n. That's exactly what we did now for the infinite potential well. Then I can plug it into here, write exactly what was written here 5 minutes ago. And now I need to find what are the CNs. Sometimes they're given, what we just said now before. When I just erased now, we have C1, C2, and C3, they're given. What happens if they're not given? Because you have something more complicated. I just said you can use the Fourier series, for example. How do I do that in general? I do this, and then once I have psi naught, I have what happens is psi equal to 0. I can do Cn is the integral of phi n phi naught. Like I can do this in order to find all the coefficients. This is basically the Fourier series for the infinite potential well. When we get to other systems, we'll learn about other functions. Any questions? Okay. So here is giving you the eigenvalue problem that we did before. And now we're starting with actual problems. Why is it called problems? People teach math and teach problems. It's a very negative word. Questions? I don't know. How is it going at home? Can you hear me well? If you have questions, do you feel comfortable asking? Apparently not. You see, by measuring, even if they didn't answer, I collapse the wave function.
Now you know.
Exactly. Paula, if you have any question, who else was there? There was someone else there. I'm trying to remember the name. Oh, I have the mouse. Ben, can you hear me, Ben? Okay. Happy to help. Okay, considering a particle of mass m in an infinite potential well of length L, find the probability of measuring the particle in the interval x plus dx at time t for the following initial conditions. Okay, these two are going to be very, very different. The first one I have here is psi 1 of x is exactly minus square root of 2 over L sine of 7 pi x over L. Okay, this means I'm exactly at energy. What did we have before? Can anyone remind me? We had my K, as Joseph likes to say, was 2 me over h bar. And my ENs were pi squared n squared h bar squared over 2 ms squared.
Right.
So what is n here? I know that
What was the mass?
what?
What was the mass of the particle?
Here? Do you need it? Well, I can see here. Wait a second. Well, here you can see if you are the first three eigenstates of an infinite potential well, the ones I drew before. They're fascinating. They're beautiful. They're signs. Okay. I can see here that n is equal to 7. How do I see that? Because my e is like n squared.
Right.
And my k is like square root of e. Therefore, my k is n. If I have here 7, then it's a 7. Okay? So that means that my n is 7. So when we're asked what is the probability of finding the particle at a certain interval x plus delta x, right? It is simply, oh, it's time t we're asked, right? What is the probability of finding at time t? So we need to use not only for a given initial condition, but also for the future, right?
Right.
Okay, so this is at t equals 0. Therefore, to find the psi of x, t is minus square root of 2 over L sine of 7 pi x over L times e to the minus I, my ENs or whatever, E7 t over h bar. Okay? E7 is whatever, plug it in. What is the probability of finding at dx? P of x is going to be psi of x t psi complex conjugate of xt times dx, correct? Okay. A good habit would be to use the complex on the left. Why? No reason. You could have done it the opposite. It's just a convention. What I get here, hey, wait a second. The e to the minus I something times e to the plus I something are going to cancel each other out. I'm going to get a 1. So all I'm left with is 2 over L sine of 7 pi x over n squared. This is a number, this is a function times px. That was easy, right? It's exactly what it says here. I really hope. Yay, it is. I'm left with this, right?
Right, because if you start in an eigenstate of the energy, you stay in the...
Exactly. If I said this is exactly what I... we see that it is time independent. This is due to the fact that the state was initial and well-defined eigenstate of the Hamiltonian. Okay, now we're going to move to something else. I'm going to be a two eigenstate of the Hamiltonian. It's going to be way more complicated. Now I'm giving another eigenstate. Here. Now I have this eigenstate. I know now that psi of x t equals 0 is square root of 1 over L times sine of 5 pi x over L minus square root of 1 over L times sine of 7 pi x over L. Okay, so can I know now what will be psi of x t? This psi of x t equals 0. What will happen in future times t? Well, that's not so hard either, because now psi of x t is going to be, I can take square root of 1 over L outside, right? So I'm going to have here sine of 5 pi x over L times e to the minus I e5t over h bar minus sine of 7 pi x over L e to the minus I e7t over h bar. I remember one of my quantum mechanics pages from second year of undergrad. I have, like, the whole page was these, me practicing to draw them nicely. Well, they used to be worse. I think that's fine, it's pretty good. But I think the right ones are way harder for me. Well, whatever. So now I'm going to ask, what will happen at times t? What I need to do is, again, do this. So I will erase that to save ink to this physics department. And I'm going to get something much more interesting. I need to take this times the same thing with the common conjugate, right? I want to first write it in a more condensed way, because writing the sign is long for me. I'd rather write it's equal to phi 5 of x times e to the minus I e5 omega 5 t minus phi 7 of x times e to the minus I omega 7 t. This is the fair choice, right? What I need to do now is to find what will be the constant here. Because phi 5 here includes square root of 2 over L. But I'm supposed to have only square root of 1 over L. So I'm going to add this, and now I'm good. Was this clear? Okay, this and this are exactly the same thing, where phi 5 is this, omega 5 is e5 over h bar, where e5 is, like, I know everything. I'm just writing it in n squared. What is n squared? That's what it's 25. I know that. 25 pi squared h bar squared over 2ml squared. Okay, this is not my function. Now I need to do this times the complex conjugate of that. So I'm going to have 1/2 times phi 5 e to the plus I omega 5 t minus phi 7 e to the plus I omega 7 t times phi 5 e to the minus I omega 5 t minus phi 7 e to the minus I omega 7 t. If there's any questions, that would be a great time. It would be a shame if you lose me now. Is there any questions? Would it help anyone if I remind you how we started? How we got here? too easy for you, right? Boring. Anyway. Sorry. Well, this here is the function as we just wrote it, and now you're just multiplying everything. He, as in my friend who wrote these things 5 years ago, 6 years ago, I have here 1/2. When I do this times that, I just have phi5 squared, right?
Right.
Phi5 squared. When I do this times that, I have phi7 squared with a minus or plus sign.
Plus.
Good, plus phi7 squared of x. Good. Now I have phi5 times phi7 plus phi5 phi7 of x both. I have here e to the I. Let's define.
It's minus.
What?
Minus 5.
Wait, I'm not that fast. Yes, there's a minus. Okay, there's a minus. Are you happy now? Okay. Now I wish you to find omega 5 7 as omega 5 minus omega 7. Okay. So we should write it here. Omega 5 7 is omega 5 minus omega 7. So I have here minus phi5 times phi7 e to the omega 5 7t. I have here plus or minus. When I do this times that, I have omega 5 minus omega 7, so I have a plus. Minus phi5 phi7 of x. Now I do this times that. I have here minus I e to the minus I omega 5 7 t. Okay, I know what this gives me. It gives me a half of phi5 of x squared plus phi7 of x squared minus phi5 phi7. If I open it to cos plus I sine and cos minus I sine, so the signs cancel each other out, I have here two cosines. So 2 cosine of omega 5 7t. And what I got here, that I did not start at one stationary phase, I started a few. Therefore, the probability of finding me at, what did I forget? I forgot the x, I forgot the x over the thing. The probability of finding me at a certain interval dx is going to vary in time. Right, left, or something. And then I can ask you, when is the best time to measure the particle if I wish to find it on the right-hand side? And stuff like that.
And we're forgetting about the complex because we have signs, right? So, in phi5 and phi7 here, if it would be a complex function, we need to make the complex conjugate.
Yeah.
But right now it's okay because we only have signs. We have real value functions.
I have no idea what you're saying. Everything here is real.
5 functions.
Here?
They are real because of that we don't need to write the complex.
When I did, if I take z, then z is always going to be real.
Right, but in this multiplication,
Like what I did here, z times z complex conjugate is always going to be real.
but we didn't make the wait.
Oh,
we-
I see.
We
Yes.
made the complex conjugate because
saying
we
here I
have
need
real functions.
You're saying here I need this,
Right,
but then now it's
right. We have to put the complex there, but since they are real functions
Yes.
or real values, we have no problem. But
exactly. Yes.
in other cases,
I think the functions of x are always real.
the size.
The function of x, the coefficient before might not be. Like there could be here minus I phi7 and stuff like that, and I could make another function, and here I'm going to have plus I, and I'm going to have minus I.
But for
Functions
example,
like this can exist, but I think for harmonic oscillator it's real. For hydrogen atom it's real. They're all real. It's
but for Bessel functions, the circle,
Yeah.
spherical potential.
I don't know. It's not in our course. You're gonna have Laguerre polynomials. You're gonna have Meath polynomials.
And
You're
those
gonna have.
are all real.
Those are all gonna be real.
Okay.
It reminds me of the cosine theorem from geometry.
Sorry, what?
It reminds me of the cosine theorem from geometry, probably because it has something to do with inner products.
Okay. I'm not able to do with this information. Sababa. Do you know what sababa means? Like cool. Okay. It can also be whatever. Sababa. Depending on the intonation. Okay. Now we're going to talk about the momentum distribution. How did I find the momentum? Now I just found. I'm going to go here. I just found before. I don't want to show you. Beforehand, I just found what was p of x dx. Now I wish to find what is p of t dp. This p is probability, and here this p is for momentum. What does p represent momentum? I teach at the high school, and my students asked me, and then I said potentum, and since then that's what I remember from class. Now, seriously, is there any reason? Latin, something? Like, most of it makes sense. I don't know, V is for velocity. A is for acceleration. Why is P momentum?
I think we should ask Newton why he did that.
You think he did it?
I think so.
Pretty crazy that he taught both of the physics and the math. Right. It describes it. Okay, how would I find this?
It's from Latin. The momentum is P because of Latin.
Okay, well, how do you say momentum in Latin?
Bele.
Hello? Okay, sure, sounds good. The way you said it sounds more French. How would I find this?
Well, you could do a Fourier transform.
Yay! Fourier transform! We're going to do Fourier transform of a function. We're going to be now, we're going to have our particle at the ground state of an infinite potential well, so I know exactly what is phi. Now, phi of x is going to be exactly square root of 2 over L times sine of, if n equals 1, I have here, what was it before? It was square to lose constant pi x over L. This is what I have. This is phi of x. So what would be phi of k?
2 deltas.
What?
It's 2 deltas on opposite sides of the x.
Why do you know this? Meaning, it's not, I don't think it's true, but why would you? What just happened in your head?
Well, you know, in the case of sine, well, first of all, for a certain momentum, for two opposite momentums, there is the same energy, so we know that they have to go together. And sine is the difference of two complex exponents, and they know that each complex exponent gives a delta function. So the Fourier transform of that is two opposing delta functions.
Okay. I'm debating whether to do it because I really don't find it interesting. I really don't. Should I do it? Is anyone interested in me doing it? Okay, you know what? I'm just going to go quickly over it in the document here. The one trick first that they're showing here, I know that psi of k, sorry, phi tilde of k would be 1 over square root of 2 pi integral of phi of x e to the minus I kx dx, right? But I'm not interested in that. I'm now interested in phi tilde of p. Now remember that p is h bar k, right? Therefore, what we try to do of p, it will be simply dividing it by h bar. So if you wish here, it gives you the formula for that. It's the exact same thing, only dividing it by h bar. It's the square root of h bar. Yeah, because I need, because the psi or phi is not the probability, it's the square root of the probability, so I need to divide by the square root of pi. So I'm going to get here 1 over square root of 2 pi h bar integral phi of x e to the minus I. Instead of k, I'm going to write here p over h bar x dx. Minus infinity to infinity. So here it shows you exactly why it is true. It shows you the formula, whatever. Delta of k minus k tag is this. Therefore, like he actually develops it. It's not very interesting because I could have just found what is the probability of finding it a specific k and then divided by h bar. Right? Is this okay? Okay, good. Like p of k dk would be phi theta of k dk. Therefore, when you do it with p, if I want p of p dp to equal phi theta of p dp, I need to define this with the square root of pi because of the square here. Okay, good. So once you do this, it does a Fourier transform and gets a certain function, not a nice function, right? What do we get? We get this thing. Can I ask you to do this in the homework? Of course I can. If you get integrals that are too hard, I'm completely fine with you writing in the homework. This was an integration by parts 4 times. I didn't want to do that. Here's the result from the computer. Fine by me, okay? I don't need you. The Fourier transform, you can say I put it in the computer, and this is the Fourier transform. What is the price of that? Because in the exam, you might need to do it by yourselves. So if you know that you're really, really fine with these integrals, don't waste your time on this. Okay. What do I like about this function? First of all, I'm going to ask you, what do you expect it to have a peak? As, what was your name before? Eliyahu. What is Eliyahu said? I expect it to be symmetrical. Because I have one specific energy. I know that going right or going left has the same energy. This is how you write Eliyahu in Hebrew. Right in English you have A, B, C, and A, B, C. So in Hebrew you have Aleph, Bet, Gimel, and you also have Aleph, Bet, Gimel. You have script and subscript. Good for you. So you expect it to be symmetrical, right? Now I'm reminding you that I'm the lowest energy level. Where do you expect it to have the highest peak? What is the most probable velocity to find? Most probable momentum to find?
So it will be low because the energy is low, and the energy could be defined by the momentum square.
Exactly. Therefore, I expect it to be, aha, beautiful! I expect it to peak at the 0. As you see, as Eliyahu said, it is symmetrical, but also it has a peak at 0. Okay? Of course, if I do the mean velocity, I also expect it to be 0, because again, it is symmetrical. But I want to know, well, if I would have the lowest energy level at a classical part, it would be simply lying here, right? Why not? What is the velocity of this one? 0. Okay. And now I want to move to a whole other thing. Ehrenfest. Are there any questions so far? Okay. We're done about Ehrenfest. I have here 2 goals. One is mention Ehrenfest because it's another concept in physics, in quantum mechanics that I cannot go a whole semester without talking about. and the other is the kind of math that we're going to do here, that you also need to be familiar with. So, what does Ahrenfest say? The Ahrenfest theorem says this. P is m dx dt. Have you shared it in class?
We prove it in the homework.
Oh, I should remember what I gave you for homework more. So you put in the homework that it's always true. Now let's see that it's true for a specific case within the infinite potential well. I'm going to have here a certain superposition of Phi1 and Phi2, a certain superposition of E1 and E2. My mean energy is going to be somewhere in between them. I want to show that the mean momentum is like the mass times the derivative of the mean location. This, of course, it reminds us of classical physics, where P is mv. It's not exactly P, it's the mean of P. Mean over many realization. This is, well, we know that P, what is P? It's something that I'm not sure if I ever showed. Probably I did. P is, of course, the integral of psi. How about conjugate?
The P operator.
P operato, psi. What am I going to write here? Dx or dp?
dx.
Dx. Or I can also do...
Yeah, we are allowed to put anything because you have not defined the base for the operator.
Exactly, exactly. That's what I wanted to see. So I can show you, I can write it as the integral psi complex of x times minus I h bar d dx, psi of x dx, or I can do
C of P.
psi tilde of k, whatever. And what am I going to write here?
K over
H bar k, which is the P operato, psi tilde of k, dk, and here I'm going to add the complex conjugate. This would be the left-hand side. Which do I prefer doing, this or this? Here I need to do the Fourier transform. Have you seen what is the Fourier transform of this thing? Are you sure you want to do this?
No, the upper one.
And of course, this is nicer, and derivative is not as nice. But doing the Fourier transform is really bad.
Right, it's
We do
a
not want to do
convolution.
Bad. We do not want to do this one. Therefore, we're gonna do this one. So this document starts with x, and I already started with p. Mean momentum. Fun. Oh, I forgot to write the initial condition. You are told that the particle starts at, I'm going to write it down, psi of x t going to be 1/2 of Phi1 of x e to the minus I e1t over h bar minus Phi2 of x e to the minus I e2t over h bar. Beautiful, gorgeous. Okay, now we need to take the derivative of each of these. It's gonna be fun. It's gonna be long. And my handwriting is not as nice as this printing.
Can I ask something about the distribution of the momentum?
Yes.
I don't quite understand why it looks like that. Because again, for a given energy, there are just two options. And here it's continuous, and the energy spectrum is discrete. So the momentum spectrum should also be discrete.
You're confusing me. My energy is definitely discrete. My
And for each energy, there are two options for the momentum, right?
why?
Because if the energy is just p squared over 2m, right, then you can calculate the momentum given the energy.
My energy here, I know exactly what it is. My E is n squared is 1. It's pi squared h bar squared over 2ml squared. This is my energy. It's a number.
Yeah, but it is if you multiply it by n squared, which is general form.
If I'm in an eigenstate, you're saying if I'm in an eigenstate of the energy, I must be also the eigenstate of the momentum.
At least in superposition of two of them, because if you look at the Hamiltonian, then the Hamiltonian is just p squared over 2n, because inside the well the potential is 0, right?
Correct.
So if you look at the eigenvalues of both sides, the energy is p squared over 2n as long as you're inside the well. So if
it probably has to do with the fact that you're assuming that you're assuming that I'm inside the well. And what happens if these two deltas are very far and they're outside the well? Mathematically speaking. So my guess has to do with that. The boundary conditions change the whole program. You're right that as long as I'm there, my entire energy is the kinetic. But the fact that I have borders affects the whole thing. My guess is it has to do with that, but it's not clear enough in my head. Okay, now I need to solve this. So for each of those.
And also the eigenvalues are discrete because k is discrete. So we have the eigenvalues of the momentum are discrete.
Yes, but in that,
the only thing is that the wave function doesn't have to be.
Good question from Michel. What I have here now is this. So, I'm sorry, I really don't know. It's like, maybe if I'll think about it for 5 minutes, I will know. Maybe if I think about it for 5 hours, I still want to know. What I have here now is psi complex conjugate. I'm going to have psi something psi. I can take out the square root of 1/2. I have two of them, so I have 1/2. I can take out the minus I h bar, right? The minus I h bar over 2. Now I have this and the derivative of that. So I have phi1, and for Joseph I'm going to write here this, it's going to make him happy, times e to the plus I e1t over h bar minus phi2 of x e to the plus I e2t over h bar. This is this. Now I need to write the derivative of that. Now, of course, I take the derivative with respect to x, so the exponent doesn't change. I have here phi1 prime of x times e to the minus I e1t over h bar minus phi2 prime of x e to the minus I e2t over h bar. Any questions?
Can we do the integration by parts implicitly? So we will get a formula direct.
I'm not sure I follow. Let's look at this. I did this, minus I h bar dx this.
Right.
And then minus I h bar over 2 here. And then I have like all those terms.
Right.
You want to do one by one, you mean?
No, you will get the same, right? It's okay.
Okay. What I have here now is minus I h bar over 2. I forgot to write the integral, right? I did. But the integral of this dx. Now let's do every integral separately. When I have this times that, I have the integral of phi1 complex times phi1 prime dx. When I have this times that, with a plus sign, I have plus phi2 complex phi2 prime dx with a snake before it. Now I have this times this and this times that. It's two different integrals. I have here minus, they're both going to be with minus? Yes. Minus phi1 complex phi2 prime e to the I e1 minus e2 over h bar t minus, well, this I'm going to leave together, plus phi 2 complex phi 1 prime e to the minus same thing. And here I wish it a friend to do again the integral of both of them together because they're very similar. I think. No, they're not similar at all, right? There's the exponent, whatever. We need to actually do this. Now, when I do the integral of this, apparently this gives me
1.
This
No,
is
I know, because it's a derivative, right? It's not.
what? I don't know what this gives me, but I do know that eventually. Oh, sorry, no. I was thinking about the derivative with respect to t. No, I'm now on the left-hand side. Derivative with t is not going to help me.
Since the derivative of the sine is a cosine and they are orthonormal, it's had to be 0.
Okay, good. This is 0. This is 0. And these two are not 0, right?
Right.
Because of P1 and P2. So I have sine times cosine, but not the same argument. I do the integral. Not interesting, right? I don't think it's interesting. Is there anyone here who thinks it's interesting? No. I do the integral, I get a number. And I have one more. I have here minus 8 over 3L and plus 8 over 3L. And it's basically the same number. So I have here a number. This is a number. Times an exponent plus another number times the exponent with a minus. This number is 8 over 3L. So I have minus I h bar over 2 times 8 over 3Ls. This was simply this, like this integral and this integral. So I have here omega e to the plus something minus a to the minus something. So
2i sine.
2i sine and have an I here. Isn't that amazing? I get something real. It makes me so very happy. So I have here 2i sines. So the 2i, the I cancel the I and the minus. The 2 cancel this. I'm left with 8 over 3L times the sign of the argument. What is the argument? It is E1 minus E2t over H bar. And have we done it slowly? We would have got, we would have seen that I have a E2 minus E1 I should have put here.
And there's also an H bar.
There is an H bar here. You forgot. You should have mentioned it. You're not following enough. Okay, this is P. Of course. Well, I have no idea how a good child examines stuff. I usually teach, I've been the TA for this course with other professors, but if I'm a student and I write this an exam and I forgot the H bar, there's some professors that will get upset at you. You got to a term, how come you didn't check units? You got to a probability, how come you didn't check that it's between 0 and 1? So here I can check and I have angular momentum divided by meter, so I get momentum, or momentum. Good. Should we do now m times ddt of x? The x is going to be easier or harder?
Easier.
Let's see. We're going to have, again, that looks shorter, right?
Actually,
It's going to be easier because you're going to have the derivative with respect to time that's going to very quickly kill these two. Because whatever it is, it's going to have an x here in between of the derivative, instead of the derivative. But okay, let's do it quickly. If I have x, it's going to be the integral dx of psi complex conjugate x psi,
Right.
which is, I had here 1/2 the integral of phi1 e to the minus I e1. Let's call it omega 1t. With the plus sign because I take here the complex, plus phi2 e to the plus I omega 2t x, and here I have other brackets. It's a good way to cheat. Too far. Okay, I have this times x times this.
I think that what you should do is like take the cursor, click this, and surround it with
Oh, like this, and then
yeah,
move it
and
here.
then you move it this way.
I think you were taught on Zoom for too long. Okay. Good. So now what I have here is this times this times this, like all the possible combinations. What I have here is a certain number. It is 1/2 the integral over phi1 squared times x dx plus 1/2 the integral of phi2 squared times x dx plus I have here phi1 times x times phi2, and phi2, there's a minus here, phi2 times x times phi1. They're both with a minus sign, as Joseph wanted to say already. Am I correct that you wanted to say that already? Minus the integral of phi1 phi2. Now I have times x e. Okay, we're not interested in doing it slowly and actually keeping track of the minuses because it's not interesting. And you have good notes here to actually see where the minuses are. What I have here is e to the minus I omega 1 2 plus e to the plus I omega 1 2. Oh, it actually doesn't even matter the order because it's a cosine. It makes us happy because they're both negative. And when I do the derivative of that, ddx of this is ddx of this. It is ddx of all this. Sorry,
dt.
t. T of all these. So this dies. It doesn't depend on t, and neither does this. All I'm left with is this, and it gives me exactly that. This is a cosine. The cosine of omega 1 to t, right? Wait a second, the derivative of a cosine has a sine. In this, I already showed that omega phi1 phi2 gives me. No, I did not show it, right? I said something else. Apparently, it's giving me h over 3l times m. Divided by m. So I still need to multiply by m to get whatever I got. So I showed that the Ahrenfest theorem holds for this specific system where I have an infinite potential well with these boundary conditions and starting with 2 whatever. In the homework, what do you have? I think they're quite friendly this time. I was like, can you press control, please? Oh, here. Fine, I don't need you. Who needs you? Okay, you have a particle confined in a well. Write down the most. You're told that it has this probability of having this energy, and another probability of having this. So the C are just the square of that, right? Now what you do not know, what you cannot know here, is there a phase between them? Is there I multiplying one of them or something like that? This you cannot know. I'm not giving you this information. But now you're told that they're all real and positive. So apparently you do know what is 5xt, and now we're asking you what are all these things. You know how to multiply them. It's with the sandwich, right? Like this. You need to put the operator. E is E, P is P, etc. Then you have probability calculation. You have here a particle that is in, you know that outside it is 0. Sounds like a potential well, right? You have here two combination of two signs. This is E2, this is E4. And you're not told what A and B are, right? Its average energy is given by E is this. Find A and B. You know that in general, my mean of E is going to be the sum over Cn squared times En. So you don't know what A is, but you know that the square root of A, like this squared times E2 plus this squared times E4 is going to give you a certain number. You can find what A and B are. What is the probability to find the particle with the energy of this thing? It's going to be 0 because it's none of them, right? What's the probability of finding it with this energy? It's going to be this squared. Sorry, this squared. Write x and p for this psi naught. Compute delta x, delta p, and show that Heisenberg was right. Remember that delta x is the square root of
x squared, the expected value squared. The other way.
Come on, are you sure?
Yeah.
It's like that.
No. Sure?
Yeah.
Right.
Okay, and delta p is its friend. Now we're asking about time development. You have here, again, a superposition of two states. Write psi of xt, psi of kt, Fourier transform. Calculate xp, and again show the time that Heidelberg and Ehrenfest were right. And now here we're going to have a sudden change, okay? What happened with a sudden change? I have here, I have here a potential a wave function that looks like this, and suddenly it changed to be like this. Now the wave function at t equals 0 is this. So what do I need to do? I need to find what is the Fourier series of this to span this with the signs of this. How many are going to be? Probably infinity, right?
Right.
And then I can do time evolution of each one of them and write to you what will be the general psi of xt here. It's going to be a sum of an infinite elements. Well, that's basically it. Thank you very much. That was another. No one's here.
I have a question about the homework.
Oh no. Is that what I did?
Hmm?
Is that what I did?
Great.